After the AC is pushed from the pump, it's going towards the drum. We're going to talk a little bit about the drums here. Lots of different configurations on drums, parallel flows. Double barrels is what you're going to see a lot of illustration here, because in the state of Virginia there are a lot of double barrel drums. One of the other things you'll see is counterflows. That's probably the second style drum that you'll see a lot of. So double barrels and counterflows are probably the two drums that you're going to see the most. Parallel flow, a little different. Parallel flow means the material comes in behind the burner and is pushed with the burner flame. Counterflow means it comes in, the material comes in on one end and is being pushed towards the burner flame. Same thing on a double barrel. It has two shells, but it is a counterflow drum. Here is a unified or a counterflow drum. You can see this particular drum here, and we're going to go over the differences of those. Here's another view of it. You can see here, material is going to be in on this end of the drum. So material is going to come down here, and then you're going to see the burner on this end. That means that's the reason for the counterflow. One of the things you see on a counterflow drum, if you're going to introduce recycle into those, you're going to see some type of recycle collar here. And this is also where your dust is put in. So this collar here is where you're going to see that. And basically what that is, that's right as you're getting ready to mix. That's where you're at in that drum. This burner's got an extended nose on it that pushes up here. And this is the combustion and the drying zone up here. This is the mixing chamber down here, and you'll see the discharge. Here's a cutaway of this drum. Shows a good indication. Here's the material that comes in. Here you have sets of conditioning flights, then you have the combustion zone, and then you have the mixing flights here. And you can see this extended nose that we're talking about on the burner, and also this recycle where the recycle's entered in. So after the material and the hot aggregate comes down, this is where your recycle would be introduced, and this is the mixing chamber. Moving back over to the double barrel. This is a cutaway at our facility looking on the inside. This is the counterflow. If you're looking, we're looking at the end that the material would come in. This is a set of screw flights. Some people call them kicker flights. That's where that material is first introduced into the drum. Those flights are designed to push that material down the drum, get it to go quick. These are conditioning flights that you'll see here. Some people will call them flying flights or raking flights, but you will see these cutouts here. Again, it's to push that material down and start breaking it up to where it can get into where it's going to be veiled and dried. If you look, there's lots of different flight configurations compared to what type of drum you have. We have a little mix and a match of old and new. If you can see too, there's also some half flights, and as we move down, we'll explain some of those flights and the evolution of flights, and lots of different flighting arrangements out there. Here's the screw flights, kind of gives you a side view. Here's some more of the flighting that you'll see. This is more of an old style design where it pushed it forward. Here's where it was put on an angle where it can push that material quicker. What you want to do is get that material moving quickly, because of what you're coming in. You don't want this material to build up here, because it'll walk out the back side of the drum when you do that. So the material's coming on down. This is where the first veiling actually happens. This is where you're going to see the veiling action. This is where the material is going to be picked up, and it's going to be introduced over the top side of the drum, and your burner flame is going to be pushing up through this. And these are old style cup flights. You can see some of them are half flights. If you're wanting to adjust stack temperature, some people call in and say, hey, I got high stack temp, what am I going to do? Well, you're going to have to remove flights, you're going to have to put flights in. And that's what that's used for. We've changed things a little bit the way we do it, but that's what the flighting is for. You'll see sometimes as you go in, every other one of these are going to be removed. What's the reason for that? Increased stack temperature. Usually if you move every other one of this first row, about 50 degrees on your stack is what you'll see. So that's what you'll see. As you move on down, this is some modifications where customers, you can see wear patterns here. This would be a worn flight. Some customers cut out some of this, again, to do a little bit more conditioning to see if they can have that material dry better. This is an Aztec design V-flight. These are half flights or solid flights. Some of the beauty of these flights is that it can reduce the amount of flights that you have to take in and out of the drum. We talked about VFDs a little earlier. You can take a VFD and you can adjust the speed of that drum to control temperature along with these flights. So you have the ability to where you do not have to muscle flights in and out of the drum. We kind of use it on the service side of it, is that you always have to remove the first set of flights. That's kind of your course correction, and then you can use the speed of the drum to do all your fine corrections on the stack temp. Some people want to wonder, hey, I always want a real hot stack temperature. Well, yeah, you want it above the dew point because you don't want to cause mudding in the baghouse, but what you don't want to do is have a bunch of wasted energy blowing out the stack. So if you've got stack temps at 300 degrees and you can keep them at 240 or 250, guess what? You're saving a lot of money in fuel on that. Here's some more older style flights. These are high TPH flights. Some people call them piggybacks because they look like they're piggybacked on top of the other. And there's different modifications for those. Here's the clips. You can see how those are welded in. And then you can see some of these are cupped on the ends and have brackets built into them. Sometimes you'll actually put a little dam on the end of that. If you need that material to retain in the drum a little longer, you could dam off one end of this. The drum is on a slope, you know, one inch for every foot, but as that material moves down, you might want to slow it down a little bit. You see this here? This is another dam, again, to slow that material down before it enters into the combustion zone. If you look, here's a cutaway. It shows the combustion flights that you see here. So the material's moved down this counterflow drum. Now it's in the combustion zone. What's the combustion zone mean? Well, it's actually those first set of flights right at the nose of the burner that move forward. This is where it's really hot. This is where you're seeing all of your high temperatures. Combustion flights are designed two different ways. There's pros and cons of both. Sometimes the material is designed to run on top of those flights to give it a shielding to keep this outer shell temperature cool. Sometimes they're designed to run under those flights to keep it cool. Most of the time people are going over the top to keep wear off of the drum shell. Here's a closer view of combustion flights. Lots of different combustion flights designs out there. These we call T flights because they're kind of shaped like a T. They have a pedestal that comes off the bottom and they're welded with clips. They can be daggered down into the drum shell or they can be gapped here at the back. Again, you can see here where they made some slight modifications where this one had a smaller gap, this has got a larger gap, letting some of that radiant heat down into that if the aggregate's going under it. You can see on this one it's designed to go over the top and then go back over on the other dam. Here's more of our conventional style. Here you can see a flight that's damaged by heat. As you get the flight too hot, it will warp and distort, and you can see the clips there. And here are the wear bars that are put under this angle, sometimes rebarb. All of that's used for is if that material does get under that on the drum shell, it basically won't wear it too bad. This is the aggregate temperature where you're looking at the aggregate as it's coming down. It's not uncommon to have aggregates in excess of 500 or 600 degrees if you're running higher wrap temps. So this is on the outer shell of the double barrel, and this is the aggregate temp sensor here where it's being, dried aggregates being put into the outer shell. This is on the outer shell, transitioning to the outer shell of that double barrel. This is the discharge places here. Here's an animation that shows the steam gases that's coming off and how they're being pulled back through. And this is where the dry aggregate is introduced into the outer shell. This is your shanks and tips here. This is where you're going to start the mixing process. You're going to introduce your recycle and your liquid in the outer shell of the drum. This is basically the injection point of the AC. So as the AC comes in, just an illustrated curtain of how the AC would fall. These mixing paddles would come up, kind of resemble what you see, type of paddle you'd see in a Pug Mill. They are different designs. You can see that there's different designs. Some of those are for retaining the material longer to give you better mixing. And you can see with this illustration here, here's the dry aggregate. As you start introducing the AC, you can see the color of it change as it moves down the hill of the drum. We get to the mixing section. This is after the liquid has been introduced. We see a lot of these chains that are hanging from this. And one of the things that's talked about in the industry is cleanup or maintenance on the double barrel. We don't like to clean and maintain the outer edge, the outer shell. This is what's been put in place to help with that cleaning. These kiln chains actually bump back and forth and keep this material very clean. We ask customers to look at this about every 50,000 tons, open the drum up, look at it. It does take some maintenance, but these, and there's different combinations of them. If all else fails, we add more chains, but these chains are basically for keeping buildup off of these areas around the tips. Here's the face of a couple of tips. Here's a standard tip, a brand new tip. Here's a tip that's worn. As that tip wears, what you do is you decrease the mixing chamber on that drum. When you decrease the mixing chamber on that drum, you affect several different things. Capacity is one of them, mixing capability, and your cleanup is a lot more when you have one that is worn this bad. It's almost worn all the way down into the shank. Here's a good view of seeing these shaggy dogs is what people call them, these chains. Some of them are called double dogs where they actually got 2 chains on each link. As the material moves on down, we always want to talk about the burner. There's lots of different configurations of burners out there. Hawk burners, Aztec burners, Eclipse. There's low NOx burners, there's open air burners, lots of different configurations. Basically all of them are used for the drying process, and they're BTU rated. Here's an older style burner, Hawk burner, probably the best known workhorse in the industry. You had the 520, the 580, and then you had a 700 series for the larger capacity. Very, very reliable burner. I guess the downfall is they were very, very loud, and also they were open air, and they could not meet requirements for some of the flue gases that you need in some states. But you do see a lot of them in operation today, still lots of parts for them. We see them, we work on them every day in the field. You could go to a low NOx burner, which is a Phoenix. This is one of our burners. It uses compressed air. It's a closed air burner, so it uses pre-mixing to do that, which gives you very, very low emissions. So it can take you to the states like Washington and California and meet those regulations. Also, there's different types of fuels that you can use in burners. Most common is gas. Fuel oil is the second, but there are also some that are using wood and some of the others. This is one that we've used to do some wood burning. You see a lot of coal burners also, so we've had several coal burners working, but right now natural gas is very, very inexpensive, and that's what most people are using because it's also very clean and maintenance is minimal. Use this animation for the double barrel to kind of go how the drum's put together, and we'll look how the material's entered in. Here's your trunnions with your inner shell and your sprocket drive. They come in sprocket drive or trunnion drive. Most people prefer the chain drive. Here's a set of wear band. This is the first wear band where the material's introduced, and here's your conditioning flights that we were talking about. This particular drum has the V flights in it, and then here's another wear band. Here's the material dams that we talked about, and then the combustion flights. There's a view of the double barrel on the inner shell. Here's the aggregate exit hose that we looked at in the slides. And there's one of the burner options. There's many burner options on them, but that shows you how the burner is mounted onto the drum. This is the trunnion assemblies. There is trunnion maintenance that has to be done. This is the thrust rollers. This is basically keeping that drum from running up or downhill. On the double barrel, you got the outside mixing chamber with the paddles, and there's where actually the AC is introduced. And that's the access door to actually get into that and work on it. Wrap inlet and the fines for the dust we spoke about earlier. And this is the insulation on that. One of the things that you see on the double barrels is that you have that steam blanket on the outside because of that wrap that comes in. So a lot of times that you're going to keep those outer shell temperatures down quite a bit because of that. Here's the gear drive on it. Again, it can be variable frequency, which will allow you to run that drum speed at different speeds to control your stack temperature with the V-flight. And that's a little bit of the V-flights and just gives you an indication of the drum turning there. And here's where the material is going to come into the inlet breeching. So as we use the animation, Here's the material introduced in, comes into the drum, hits the first set of flights that's going to move it, push it downhill and break it up, and then it's going to go straight into the veiling flights or the V flights. This is where you're going to see your veiling. This is where that hot air is going to come through and take the moisture off of that aggregates. As it moves down the drum, it goes into the combustion flights that you're going to see next, rolls on top of the combustion flights, then it exits into the outer shell of the drum. Once it exits into the outer shell, this is on the mixing. This is your kicker flights that moves the material straight to the first set of mixing tips, and the material is pushed up the drum. This is showing an illustration of the recycle coming in on the outer shell, and you can see here's where the recycle comes in, and you can see these shaggy dogs or these kiln chains here that are moving back and forth to keep that amount of wear down. You can see some of the dry aggregate mixed along with the recycle. Now you're going to see the AC being injected in, whether it's through a warm mix system or if it's going to be injected straight into the drum. You can see here where the mixing is taking place. Here's where you're bringing dust. Again, taking all that material we've talked about and the steps we've talked about before, this is where everything's being introduced into the drum. We talked about a little earlier, feeder delays and point of mix times. When we say point of mix time, this is what we're talking about. We're talking about when all of the raw virgin aggregates and the recycle aggregates, the dust and the AC are introduced into the drum. So anyone that talks about point of mix time, that's what you're referring to. After you see the mixed product, this is the discharge, and then as it's the finished asphalt is being pushed into the drag. Another configurations you will sometimes see to help with running higher wrap, they will actually introduce a Pug Mill or a small mixing drum. You're not seeing as many of that configuration, but it is starting to be introduced into the industry. And basically what you're using is you put wrap in the outer shell and you introduce your liquid into the Pug Mill. And some people that may have been on a batch plant or have been around a batch plant, they say, hey, that looks a lot like a Pug Mill on a batch plant. Well, it is. It just doesn't have the ag hoppers and stuff above it. It's a twin Pug Mill to allow you to run higher wrap content. And this is kind of a view of that, just to kind of give you an illustration. But once the material leaves the drum, it's going to go up to the drag and go to the silo systems. We're going to talk a little bit about that. Here's a drag going up to multi-silos. As it conveys the material up to the top of the silos, according to what type of silo configuration you have. You can have 1 silo, 2, 4, 6, 8. We've got as many as people, some 9 and 10 silos. Most of the time, pretty conventional is 3 silos. Sometimes 3 to 6 is what we're seeing most of the time for storage. Once you get up to the top with the drag, you have traverses, which can be horizontal or they can be inclined, and it can convey the material to the batchers. Here's an illustration. We talk about segregation. And this is a model that we use to help with segregation. You can see that we want that material to fall in the center of that batcher. The better that material discharges into the center of that batcher, you can see the more uniform that you get, as far as the red being the larger aggregates, the blue and the green being the small. You want that batcher to fill up. The batcher is very important for segregation, and we'll talk about that, but this is a good indication of how you want that material to fall into that batcher. You don't want it to fall anywhere other than right in the center. Here's a view from the bottom of the drag, again, a model. You can see the material that's coming up the drag is very uniform on the slats, on the drag slats, and the material is discharging right into the center of the batcher. That's what you want to do to keep segregation at a minimal. Outside view of the batchers, here's a couple of batchers with a traverse in between those. You got flop chutes. Some of the batchers have some top gates on them, or the open gates here. And we talk about silos. You have 2 different types of silos. You have surge bin silos, and then you have storage silos. Surge bin silos are basically what they say. They're just for short temporary use of production during the day to hold the mix in. Storage silos have the capability of storing mix several days. And they do that by basically keeping the oxidation down, no oxygen getting to the mix. Here's a view once it goes into a triverse. Instead of dropping straight into a silo or into a batcher, it's going to be conveyed with a triverse. And you can see that this material is being pushed over into the center. On this particular one, it may have been pushed a little too far. If you can see, you're getting some segregation here. You're getting a lot of the larger material on this side. There is some maintenance that you've got to work on these batchers. They're very important. Again, you've got gates that have to be maintained. You've got bin indicators, and you have solenoids. But we talked about it a little bit already, but why is there a batcher? Well, the one fact that you always know, it's the easiest way to prevent segregation as long as it's being used correctly. And we see this more times than not. Poor maintenance or things like that will cause segregated mix. You can do a fantastic job of having a lab that makes a great mix design, an operator that controls the plant very well, but a batcher not being maintained can destroy a good mix. And it's not that it was the operator's fault or anything else, it was just on the maintenance of the batchers themselves. Some of the deadly batcher sins, batch not large enough. If you're using a small batch, you make too many small drops. It's not good, it segregates easily. Batchers not loading in the center like I showed you in the illustrations. Batchers loading at an angle, meaning it's pushing it up one of the outside walls, or maybe it's an offset and it's pushing it on the inside wall. Gates not closing on mix. If you walk up to a job site and you hear the batcher and you can hear material running through the batcher, you know that's a good indication that it's not giving it a cushion. It's allowing that material to flow through the batcher straight into the silo. That long fall causes segregation. Mix levels in the silo maintained at high level. Some people say, hey, I want to keep my silos full all the time. Well, we've got some illustrations in here that show you that's not always the best thing to do, that can cause segregation. So we'll show that. And then batcher gates not being maintained. That's the 7 things that you really want to look at. Here's a comparison, which is the original configuration of the material being pushed over to the side, and then a modification made with that material being pushed straight down. Again, center loading of the batcher is crucial. Here's the offset loading that we're talking about. It's pushing it to the outside of this batcher, causing segregation on this side of the batcher. Here's the angle loading, means it's pushing it to the outside wall, and again, you can see the segregation on this outside wall. Again, things that you want to eliminate at a plant to keep segregation at a minimum. Here's what you would see if you had a batcher gate opening only on one side. You do have double gates on those batchers. Again, that's a good way to cause segregation because you're going to get buildup in here, you're going to cause slope, and it's going to allow it to segregate inside the silo, which will give you failing test results. We talked about surge bins. You can go into a portable plant where you have this drag style here, and you have a SEB or a surge bin. Has the same principles though. You have a batcher at the top, which is here, same principles, and then you have the surge bin here or the surge silo, which is low capacity, somewhere less than 100 tons. Most of the storage silos that you see are going to be 200 to 300 ton storage silos. As you've got the product made and you've got it stored into the silo, the next thing that you've got to do is you've got to take care of the silo loading or load out and the truck loading. Again, you can actually destroy the way mix has been processed with this loading if you don't load properly. This is the bottom gate. You see a lot of different gate configurations on the silo. Same thing applies. You have to make sure you've got good gates operating at a good constant speed. You want to inspect those regardless if it's a single or a double or if it's a sliding gate or a clam gate. End of the load coarse aggregates. How did it get there? There's a thing that you see in the back of a dump truck that some of this aggregate actually fell back into this corner, and this aggregate could stay in this truck, and the coarse aggregates could get pushed in those corners if you're not loading the truck properly, which again can indicate a segregated sample when you're testing. You kind of see these signs or placards all around asphalt plants, and I don't think it's said any better than what these placards say. It actually shows longer truck beds get more drops, but it is the ideal way to load mix into a truck to keep segregation minimal. You always want to put your first drop on the front of the truck, then you want to come back and put your second drop on the back of the truck, and then your third drop goes right into the center of the bed. And again, longer you get on the truck, the more drops you'll get, but you just want to keep that back and forth between that to keep from getting segregation. Improper truck loading can cause, if you do a single drop, if you do this single drop, it gets angular and it pushes all this coarse material. It'll tend to roll to the corners, and that's what you don't want. The first picture we showed that coarse material getting down in the corners of the bed. So that's what you do not want. So single drops can be done, but it takes a good combination of a great plant operator and a great truck driver to make that. So you have to be very careful doing single drops. The first drop is crucial. You always want it, like we talked about, you want it on the front of the truck. You want it right up on the cab. You want it in the front of that bed. It fills up this void very quickly, and it doesn't allow any of those coarse aggregates to run down into it. Here's a good indication of it where it's pushed into right up at the front of that bed. Here's your second drop. You put your second drop the same way. You want it to fill all of the voids in the corners of those beds. Put that drop on the back. Now you've got a drop on the front of the truck and on the back of the truck. And then your third drop would be in the center. Again, eliminating the place for voids for those coarse aggregates to roll into. So again, putting that third drop on. If you look at the back of this truck, that's a great way to show of a properly loaded truck. You got the first load up on the front, second drop on the back, and third drop right in the center. That is textbook way to do good loading into the truck. Here's another view of it. Again, you can see that first drop filled all the voids. And you can tell by the hump that is where the first drop was at. After loading, you really got the completed product going out. One of the things that you don't see a lot in the state of Virginia, especially for VDOT work, is batch plants, but we are going to cover the batching plant just a little bit. The same principles. It still has cold feed bins. It can have wrap bins, but the biggest change that you see is that it has a batch tower, and most of the time it's going to have a hot elevator instead of a drag, and we're just going to cover that real quickly, but I do want to cover the batch plants a little bit. Very little VDOT mix is made through the batching plant. Most of it is through continuous plants. Here's an illustration of a batch plant. A lot of the things we talked about, cold feed bins, asphalt storage tanks, the bag houses, the primary collector, all of that's the same. You got a dryer. The big change that you see is the batch tower and the hot elevator. So a little different way of doing that. In Europe, batch plants still rule. They are still the #1 style plant to have in Europe. Here's a batch plant, gives you a good side view. You see the hot elevator that is placed right here. This is where the aggregates now, or the dry aggregates leave the drum, go into this hot elevator, and they're conveyed up to the top. You got a shaker deck on the top. That shaker deck does a couple of different things, and we got an exploded view here. It separates that material. All that material's been dried. It's got screens on the top for this screening here, and it pushes it down into hot bins. You got a fine hot bin, and then that, kind of like our cold feed bins, we had all of the cold feeds separated, and we introduced them into a mix design. We dried them all and put them back together, and then we introduce them into the batch tower and we separate them again. So one of the things that you see in the U.S. is that a lot of people think that, hey, a batching tower, it really causes a lot of extra work and a lot of maintenance. And in some aspects it does. It definitely has a place in the market. It is great for making small trials of mix. It's really, we call it the mom and pop business, where someone has a small niche to where they're in the industry to make mix very quickly in small amounts of it. They are ideal for that situation. But you do have hot bins, and you can have several hot bins in these plants, bins 1, 2, 3, and 4. Then you have bin draws down here to proportion it from the batching control or the mix process or the blending control that we talked about on the continuous mix side of it. Again, still utilizing PLCs and things like that. One of the things that you've seen people do though here recently over the last several years is that they are basically running a batch plant like a continuous mix plant. What they do is they use a blending control to blend the materials. They take all of the screen decks off the top. They basically don't even look at the individual hot bins, and they put all of the aggregate already designed, already mixed into the batch tower. Then they do one gate pull, and basically they turn their batch plant into a continuous mix plant. What does the mixing? You have dry times. You have a dry time where the material is introduced out of the ag hopper and the recycle hopper. It goes into the Pug Mill. When it gets into the Pug Mill here, this is where the mixing time happens. You have a dry mixing time of a few seconds usually. Then you do a pull on the AC pot or the AC bucket, which is illustrated here. And you pour the AC into the Pug Mill. And then there is a wet time, what they call a wet time. Then it is discharged into the truck. Another thing that you see like this is a plant. I think this plant may be it's in Europe or Iran. I can't remember exactly where it's at, but this plant's showing that you're batching straight into the truck. So you have that capability of batching into the truck. But if you see on the left-hand side of the photo, we have a drag there too, where we could convey the material up to a set of storage silos. And usually what they do is they will pull the truck out of the truck dump. They will pull in a receiver. This can be done a couple of different ways. It can be done with a chute. It can be done with a traverse. It can be done with a hot belt. There's lots of different ways of conveying that material over, but most of the time it's got some type of receiver to carry that batching mix up to the silos. That's the end of my presentation, and I'd like to thank you.